Okay, so at the end of the previous video, I gave you this question: what is the 95% confidence interval for the returns to education? We have point estimator, we have standard error. So this is enough to calculate the confidence interval, especially when you use 95% confidence level. You have to use 1.96 but like multiplied to the standard error. So it goes like this, right? Point estimator plus minus z alpha over 2, right? Error, z alpha over 2, which is 1.96, and standard error. You have all the numbers. It's pretty easy to calculate that. And then if you do the math, you get these intervals, like this interval. So that means the returns to education looks like greater than $0.65, but less than $0.83. It's somewhere in between them with 95% confidence level. Okay, that's how you calculate that. And one more thing, like now from the same estimation results, I would like to test if education matters in wage, right? I just assume that our education does not help make more money. So you calculate the t statistic and try if you can reject the null hypothesis or not. Okay, these two numbers and two-tailed test hypothesis should be enough to calculate that. Remember, the t-statistic is the standardized difference between your estimator and your hypothesis. Your estimator is 0.743, your hypothesis is 0, that calculate the difference, and standardize it by your standard error. Divide the difference by 0.046. That will give you 16 something, right? If this t-statistic is close to 0, then you don't need to reject the null hypothesis because the difference is small. But if the difference is too large, then your hypothesis is not consistent with your data, so you have to reject your null hypothesis. Okay? Then what is the threshold for the decision? That is 1.96 again. Because we are using 5% significance level, you have to use the standard normal distribution to find the threshold who has outside probability of 5%, that is 1.96. So if the t-statistic is greater than 1.96, you have to reject the null hypothesis. So you have to reject the null hypothesis in this case. The answer is C. T-statistic is 16.152. Okay, this is what you get, and the p-value is 0. If you wanted to use p-value approach, it's also same. Then let's compare. We just calculated t-statistic of beta 1, 16 point something, and p-value is 0. P-value was calculated and confidence interval was calculated, right? We just calculated these four numbers from these two numbers, right? So Excel kindly calculate those numbers for you. So in the end, in the future, you don't need to recalculate these things again. You just need to tell if it is rejected or not, but you need to understand what they mean. And one more thing, actually the numbers are slightly different from what we just calculated, right? The reason is because what we calculated was 16.152, but it shows 16.296. So the difference is first rounding errors, right? Like I only use the third decimal places, but when you divide by the standard error, actually the decimal places matter a lot. That's the first reason. And second reason, when you calculate the p-value and the confidence interval, I approximated everything to the normal distribution because that's good enough. But Excel uses t distribution, which is different, slightly different from the standard normal distribution. So there could be a small difference that's not much different. Like it's like 0.653, but if you use t distribution, it is 0.654, 0.001 approximation error. Even the upper limit does not change, right? So there is a very small rounding error and approximation error. I don't mind. I don't think it's a big problem. So I'm telling you, there can be small difference, but does not cause much difference. Now let's move out of the simple hypothesis. Like earlier, we only tested if if the education matters or not, its effect is zero or not. But you may have other kind of hypotheses like this. I believe that the returns to education is greater than $7.7. So I want to reject this null hypothesis to argue that the returns to education is greater than 0.7, right? My plan is I want to argue that it's greater than 0.7. So I set up hypothesis testing in this way. Okay, so then how we have to recalculate everything again. The t statistic we calculated was based on two-tailed test about 0. But now we are concerned with upper tail test at 0.7, right? So they are different. So, but it's not that different. You try this. Try to calculate the p-value based on this upper tail test. Pause the video now, and if you need a reminder, you can just open the slide from chapter 10. Yeah, right. Chapter 10, we learned how to calculate the p-value for an upper tail test. Okay, so we have to follow several steps. First, you calculate the t-stat, and then you calculate the p-value based on the standard normal distribution, and then like you don't make decision here. So first step is to calculate the t-stat. T-statistic is the standardized difference between your point estimator, your data, from your hypothesis, 0.7. So the difference is 0.043. This is the difference, okay? And you standardize it by the standard error, which was calculated from Excel, right? Then if you calculate that, your t-statistic is 0.93, okay? The difference is slightly smaller than the standard error. And then it is an upper tail test. So the p-value is based on probability greater than the realized t-statistic, right? So you only care about the upside, right side tail, right? Upper tail. So if you use Excel, if you use a calculator to calculate the standard normal distribution, it turns out to be 17.6%, approximately like 7.6%. So the p-value is 17%, which is like sufficiently large enough so that the null hypothesis is not rejected. So you wanted to reject it to argue that the returns to education is greater than 0.7, but unfortunately you could not reject the null hypothesis, so your argument cannot be made based on this data. Okay, so this is how we apply confidence interval and hypothesis testing to regression estimators. So the idea is simple. The same. I just apply the same ideas again and again. And Excel calculates most of those important statistics for you. However, you should be able to interpret them, and you should tell what it means, or how to interpret them, and how to change them when you need to implement another hypothesis testing in your context. Okay. So that was part one. And part two, prediction. When you prediction is pretty straightforward. We predict Y, like so you have estimated fixed cost, estimated marginal cost, right? And X is like output you are willing to, you are going to produce. So if you are going to produce X, then you can predict how much you are going to cost, how much it costs, if you could estimate the cost parameters, right? Given the cost parameter estimates, you can calculate, you can predict the cost. We call that, in statistics, we call that fitted value, right? The Y is fitted to X, right? And in our example, of like the original example, simple example of cost and output, the fixed cost was about 8.2, estimated to be about 8.2, and the marginal cost was about 2.38, right? In this case, we can predict the total cost when you produce 6.5 units, right? Then, so 6.5 times marginal cost plus fixed cost is your predicted fitted value, like predicted cost or the fitted value. Okay, remember, we never observe 6.5. So from the data, from the original data, let's look at this. From the original data, we do not observe 6.5. We observe 5, like 6. We observe 6 once. We observe 7 once. So you may use only these two data to calculate the predicted cost. But our estimator is better. Regression model is better because, like, if you use only 2 observations, your sample size is 2. Right? 6.5 is somewhere in between them. So that's only 2 observations. But regression model use all data, right? Like 12 observations. We obtained this prediction from 12 observations, which is much better, much larger information to make this prediction. So regression model is better in that sense. It's more accurate and more reliable statistically. Okay, so we are estimating 6.5 here, not using only these two numbers, but using all the numbers, right? All the observations, and making a larger straight line, not just from these nearest points. Not simply looking at the 2 points, but looking at all the points at the same time. So we obtain where the line goes through at 6.5. That is your predicted line. And again, the important intuition here is that when you estimate this point, we not only use the nearest observations, but use all the observations at the same time. So it will help you get better and more accurate, reliable predicted values. So that's the reason why we learn statistics and why we use the regression model. Okay, then try this. So, like, we have OLS estimators, and you predict the total cost when you produce 5 units. Okay? So given those numbers, it's pretty simple. We calculate beta 0 hat plus beta 1 hat times 5, right? So you just need to calculate this. It's simple enough. And what you see here is you can actually predict the predicted cost for each of the month, which we already observed. But we calculate their predicted cost. So then you see the differences. In January, we observed $15,000 as the whole cost, but it should have been like smaller, 12.96. So approximately 2 is some kind of error. We spent additional $2,000 somewhere in January, and in March, in February, our observation was same $15, but our predicted was 15.34. So your prediction is different from the actual cost. That will give us the residuals, right? Residuals are the difference between the actual observation from the predicted cost. And remember, we already have the residuals here. So for each observation, we can recalculate the predicted costs, and then the difference between the prediction and the actual observation becomes the residuals. Okay? And they are the difference between those predicted and the observations. The differences between the red and the blue dots imply the residuals. And we are going to use those residuals to evaluate how good your model is, how accurate your model is. Okay? So if your model is very, very accurate, there will be very little small residuals, right? Your prediction should predict the observation perfectly if your model was perfect. But of course, there are errors. So anyhow, the smaller the better. That is the key idea. We have residuals, but we would like to have the smallest possible residuals. That's our idea for the next step analysis. Okay, so the residuals are calculated like this. And statistically, residuals are a new transformed random variable. Remember, when we learned the variance, I explained the squared deviations are just another random variable, a transformed random variable, and we have as many observations of deviations as the original variable, same as residual, right? Residual is basically kind of deviation, so we have like as many observations about the residuals as the original random variable. So we are going to use this residuals as a new random variable, and we will do something very interesting based on the residual. Okay, so I will stop the video here, and we'll continue how we utilize the residuals in the next one. So see you in the next video, and thank you for watching.